Hey, John here. Let's look at some of the modifications I made on my RISC-V, the RV32i simulator, to accommodate the ability to run with multiple hearts, okay? And I'm going to use the word heart in the context of this discussion due to the simplicity of this simulator. It is synonymous with what I would think of as a core, okay? These RISC-V 32i cores or hearts that we've implemented here in this project are very simple. They don't have a cache. They don't have a lot of resources that could be shared amongst each other. So these are very simple logical units here. So to create two of them and call them both hearts is fine based on my understanding of the RISC-V architecture. Because we're just not that sophisticated. So it's really the same kind of thing as a core. All right. So what did I do to mine? Well, I changed the constructor to remove the argument in here. The last version of this, we had RV32i class constructor. We had to pass it a reference or an address of the memory object. In order to create an array of RV32i objects, I had to create a constructor that had no arguments here, right? So I can create an array of these now and then come back to each element in the array and call setMem and give it the address of the memory object that way, okay? That's the first modification. The second one is I created this setID method, which I then use to store in a private variable that we'll look at in a second, so that we can assign a unique ID number to each one of the hearts, okay? Now, while I do this, I also come in here and I create this string value that I keep in another private member function called ident, which I use to mean identity. And the string is created like this. There's an open square bracket, a number, a decimal number representing the heart ID, and a closed square bracket, all right? So anytime I want to print anything, I'm going to prefix that print line with the identity of which one of these hearts, which core, printed that line, okay? We'll see this when we run it in a minute, and you'll see that, you know, when core 0 does something, you'll see a 0 in front of it. And a core number 1 runs it, or heart number 1, you'll see a 1 in front of it, all right? So we can tell which part of the which one of the hearts in the CPU is doing the printing, okay? Then down here, when I wrote mine, this is actually like used from assignment 4 and assignment 5, as well as this current one. So I got these if-defs that I use to bring in whether or not there's a simulator in here or just, for example, a disassembler, okay? And you'll see a couple of these conditional things. When I compile it, I define this. So this is all part of the system. We have the run and the tick that we saw before. We have the various set routines that we use to set various parameters. I have extra options for mine, like whether or not to actually do and execute branch instructions versus just show them and then just skip over them, which I use for some debugging when I was working on my simulator. Okay, so this defaults, of course, to true when this thing runs. So by default, it works the way that the assignment 5 simulator ran, okay? I added some get routines so we can get these various things, because as we'll see in a minute, the main routine needs to be able to ask what's your instruction counter and your heart ID and stuff like that. So it can print out extra stuff if it so desires. These are just simple little accessors, right? Reset, dump, all this stuff down here. This is all the same stuff that we've seen since we wrote a disassembler. Nothing new up there, okay? Here's all my exec functions and stuff like that. The other thing that I added, we're going to add one single new instruction that we need in order to support our ability to run more than one heart or core at the same time, okay? And that's going to be this instruction, the CSRRS instruction, all right? And we'll take a closer look at what that does in a minute. The bottom line is this particular function, the only aspect, it actually can do a whole lot of things. The only aspect of this instruction that we support for this project is simply to allow a running piece of code to ask which core, which heart is executing this instruction right now. Okay, this is how each one of the pieces of code can figure out which heart it's running on. All right, that's what we use that instruction for. So what else did we add in here? We added, these are my flags for the whether or not I'm supposed to do the various things, same as before. This one's special for my thing that I added for debugging. So what did I do? I added a heart ID and I added the ident string. Everything else in here is the same as it was before. So in conclusion, I removed the required memory pointer from the constructor. I added these two variables. Okay, and I added a way to set the memory pointer after I construct the object, and I added a way to set the ID. All right, that's the main gist of the whole thing here. Yes, I need to also be able to read the values of some of the stuff from main. Okay, let's look at the implementation of these items here. Okay, this file is the exact same as it was last time. Got your reset, you got your run in here. My run includes some extra stuff, like whether or not I actually go to the operating system and get the clock time, and I calculate how long it took to run the simulation, and I can say here's how many nanoseconds and how many instructions per nano on average, and blah, 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 blah. So mine has a little bit of noisy extra stuff in it than the one that you might recall writing yourself. This is the standard tick routine, okay, that we've all seen and know and love. I added this right here. Otherwise, this is the same as the assignment. Because what's going to happen is when we have multiple hearts running, one of them might halt while the other ones are still going. And rather than just simply saying halted, halted, halted constantly, what it's going to do when the tick routine is called is nothing whatsoever, and it will be silent. So once a heart is halted, it will just go away and its output, there will be no more output printed from it, okay? That's what I added this thing for. I guess I lied. There's one other change. Like I said before, every one of the things that get printed now from my RV32i class, it will be prefixed with the identity of which one of the hearts, which core, is printing that text line, okay? So because I print out the program counter right here, well, it's got to be prefixed now with the ident, okay? You're going to see that in the dump routine as well and everywhere else in here. So what does the dump routine do now? Well, when it dumps the registers, I modified the register file dump method to include a string, a standard string reference, and so that when it prints out the registers, it will print the heart and the core number in front of it. When I print the program counter, I print out the identity, which is the heart and core number. Okay, we get the general gist there, okay? Here is my new instruction, okay? What does this thing do? You should recognize this. This is how all the execution routines are. Get all your input parameters and condition them as you want. Check them and you know, prepare to do the operation. What's going to happen in here is when you execute that instruction, it has parameters. One of the parameters, it's an type I instruction. We'll take a little bit closer look at it in a minute. But the bottom line is it has an immediate operand, which is this numeric value, and we simply say, look, is the it has, you know, 000 through FF as its values, because that's what you get in a 3-digit IMMI operand, okay? Because I masked off the sign extension over here, I can treat it as a 3-digit hex value in this part of my code right here. And what those are numbers, okay? Just simple numbers of registers that are inside the CPU that allow programs to ask questions like, hey, does this CPU have an A extension? Does it have, you know, does it have a floating point unit and stuff like that? All right, there's a bunch of codes in here that it can ask about this system. Well, if it asks to see what we call register number F14 is, what it will do is it will set the destination register when it runs to the ID of the heart that is executing this instruction right now. And you can kind of see that right down here, all right? So what happens? I have to make sure that I don't screw up and do the wrong thing. This code only supports this one register, and it only works if RS1 is 0. Okay, so if the immediate value is not F14 or RS1 is not 0, I'm going to just halt it and consider it, like an illegal instruction. I'll go ahead and print it out if we have tracing in the usual way. How do we print this thing out? We do it the same way we always do. We call our usual render function. We can look at that in a minute. We then, pad it with spaces, and we throw a comment over here that shows what the side effects of that instruction will be when it runs. And that will be that the destination register will be assigned a value of the heart ID. That's all that we're going to use this thing for, right? So then down here I say that if I'm not halted because this thing croaked or something, go ahead and actually do it. Set the destination register to the actual heart ID for this particular object that we just looked at and saw how they're assigned by that method there. Add forward to the program counter. We move on our merry way, okay? So let's now search for the render routine. This is going to look like any other render routine for any other instruction here, right? So what's he going to do? He's going to get his parameters just in the usual way. He's going to format the mnemonic with the, here, there's your mnemonic. You got a destination register and so on, the immediate value, and the RS1 register that will appear along with it, and it would print it out, or at least return it as a form of a string, I should say. It doesn't actually print it here, right? For doing disassembly, we have just a simple switch statement for those of you following along at home based on the opcode. And for those instructions that have a func3, which becomes kind of like part of the opcode, we then further decode the instruction. So if we are executing a system instruction and the func3 is, is 0, then we're dealing with ecall and eBreak. Otherwise, I've defined a constant in my RV32 header file that is for the func3 code that represents the CSRRS instruction. And if it's that, I go ahead and render it, right? Let's take a little look here in RVLP. I added these instructions very recently to this document. So here's the function, and you can see all these system thingies as the same opcode, as you can see, of ecall and eBreak, just like that switch statement suggests. There's the instruction. There are the operands that it has. CSR is the IMMI value. That's this over here, right? RS1 in the form that we're using it, we have to have a 0 in there for the way we're executing this function. And RD is where the heart number will be stored. Okay, here's the func3 value. If you want to know, in binary 010, that reflects the sub op code for this instruction right here. Okay, that's part of that decoding in the switch statement that we saw right here. Okay. Now, that's for disassembling it. If we just search for this, we'll find out there's going to be an execute in the, well, there's the rendering routine, right? There's the switch statement for the execution, which is a very, very much same structure that we get for just simply disassembling, all right? So for those of you following at home, the insight here is, how do we decode an instruction? We just put a big switch on the opcode and deal with the, whatever it is, half a dozen or so opcodes, and then we have a sub switch to deal with all the func3 values to further decode them, all right? And you can see this is exactly like it is for just simply disassembling, but this one's going to execute it instead. So we see again, we have a system instruction, we got a CSRRS, go ahead and execute it. We just looked at the code. If you want to know a lot of details about what this instruction really does and how it works and what the other 4,000 registers are, you can download a copy of this thing here. It's the RISC-V Instruction Set Manual, Privileged Architecture. This is a draft from last summer. The last official one was in June of 2019. So this is a moderately, whatever updated version from that. I'm going to just do a search on CSRRS. And in here, it'll talk about how these registers work, what they do, and how you're supposed to get the values out of here and all this other fun stuff. All right, I'll leave that as a task for the viewer to go ahead and read all this if they really want to. What we want out of this is the ability, let me do a search on mHeart ID, right? So in the register, we say, oh, look, these are the machine level CSRs. I don't remember what that, control and status register, okay? So if we click on this, it'll tell us there's a register that stores the ID number of the heart. And if you read in here, you can find out that the way this is phrased is kind of weird. At least one heart must have 0, have an ID of 0. What they mean to say here is exactly one heart must have an ID of 0, because all the heart IDs must be unique. Okay? The rule is you have to have one and only one heart that has an ID of 0. Okay? And every heart ID has to be unique. That's the only rules. And they actually point out the fact that heart IDs might not necessarily be numbered contiguously in a multiprocessor system. Okay? So it could be you have one that's 0 and one that's 105 and another one that's 902 and so on. To me, that makes no sense, and it complicates things. So in our simulator, the rule will be a subset of this rules, okay? We're going to have one heart that's 0, a heart that's 1, and a heart that's 2, and so on. For as many hearts we want, they're going to be orderly. They'll start with 0, and there will be one heart for every integer starting from 0 counting upward, all right? And we'll see why we want that when we start writing our code. If you're on a real system that doesn't number their hearts that way, you'll have to create a table and save them all in there perhaps, and perhaps even relogically number them in your code so that they're more convenient to access if you want to use them the way that you're going to see me use them in the code that we're going to look at. This CSRRS instruction allows us to read this register, okay? You can read this manual about all the other things that it can do. All we care about is I want to know the value of that heart ID, and I want to be able to get it into a register in my simulator, okay? That's all we care about. And in order to do that, this is the code to make it happen. So you've just seen all the RV32i mods. Okay, so where do the other modifications take place? Well, we already mentioned that the register file has to print out the identity when it runs, right? So in my dump routine, I added this parameter here. And each time we get to a beginning of a line, I print out, I call it header, okay, as I print out all the registers. If you screwed yours up and didn't space it out right, pause this, go back and fix your code, okay? All right, what else do we got? Main. So main is where really everything takes place here. So let's look closely at the main routine. How did I get all this to work? First of all, I added more arguments to my simulator and stuff like that to deal with this. The number one most important one is how many hearts do you want to simulate with a default of 1. So the way this simulator works is if you don't say anything about it at all, it works just like it did in assignment 5. The default is 1 heart. When I run with 1 heart, as we'll see, I never bother to call that set ID function, so it defaults that heart ID to 0, okay? And when it runs, because I never call the set heart ID method, it never formats the identity, and the identity then is there for an empty string, and it doesn't print it out at all. Like I said, by default, this will output and look the same as it did in assignment 5 if you never bother to specify any hearts. So the default number of hearts is 1. If I'm going to, in here I have this multi-core if-def, that surrounds the new code. So I can compile this to be assignment 5 as well if I want to. The additional argument here is the number of hearts if you specify the H parameter, which I added up here into my GitHub string, okay? What else is going on in here? This is all the same stuff. Create a memory, load the file, and if that fails, show the usage. I have a special argument to my simulator that allows me to tell the memory system to not allow anybody to write into a region of memory underneath some address. I use that to help debug my simulator. You should have probably been doing the same sort of thing if it occurred to you when you were developing yours as well. I just left some of the debug routines in place. I just don't use them. Just FYI, you'll see some extra parameters in here that I found useful at some point. So in here I see if-def multi-core. I see a bunch of code in here. This is what happens if I want to run with multiple hearts, or I want to compile it that way. And then down here there's an else, and you should recognize the stuff that's down here that is basically what we did in assignment 5. So there's your assignment 5 main routine. create a simulator object, set the memory. I had to change mine. Remember, I changed it. Yours probably says RV32I sim open paren mem all in one line. But because I changed the constructor, I can't do that. I have to do this separate thing down here. Now I asked, did the show assembly flag, was that on? If so, go ahead and do it. Reset the RV32I object. And then down here, I have another compile, so I can actually compile this like assignment 4, where it just does a disassembly and nothing else. So what happens when this thing is on? Well, this is your assignment 5. Here's one of my special options that I can use to turn on and off the simulation of branching. You don't have that. By default, it's true, so it'll just run like it does in assignment 5. These are the ones that we have. Show the instructions, show the registers. When simulating, right? I even have a show simulation that I can turn off, which is also not part of assignment 5. So I can actually tell it not to bother showing the simulation if I want, which basically makes it run and act even like assignment 4, even when I have the simulation logic compiled in, all right? And if you want to see the, the Z option sets this flag right here, which will dump out all the registers in the memory at the end. Okay, so that's what we started with. And I ended up hacking up the code enough, and I said, that's not worth doing. So I have this if def up here, right? So if I have a multi-core, I have a completely different set of code to accomplish the same thing, right? So what happens? If I have multiple cores or multiple hearts, right now, these are synonymous because of the simplicity of this system. I have the sim pointer that is going to be assigned the result of a new operation to create an array of RV32I objects, one for each of the number of hearts that I want to put in the system. By default, that would be 1, right? So then what do? I go for each heart in the system. I need to set the memory pointer because these are going to all be running with the same memory. This is literally shared memory. This is an example of a shared memory system. Okay, why? Because we're sharing the same memory with every one of these cores or hearts, as the term might be. Okay, so then I ask if the number of hearts is greater than 1. Then and only then am I going to call the set ID thing in here. Remember what I said: if I don't call set ID, that ident is set to an empty string, so the output will perfectly match that of assignment 5. If I run it with only 1 heart. If I run it with multiple hearts, I then call the set ID so that one of them will be a 0, one of them may be a 1, on up to the number of hearts, right? So I in this loop is for each one of the hearts, okay? Now for every one of the hearts, I need to set all these same flags for every one of them. So sim sub I, show instructions, show registers, and whatever my other custom special options are. I need to do that for every heart instead of just for 1, right? Okay, if I want to show the disassembly at the beginning of the program, well, just pick any old random heart and say disassemble the thing, all right? Now remember, when we do the disassembly, that it will modify the PC register variable in that RV32I simulator object, right? The RV32I class instance, okay? So I have to remember the key is I got to reset the thing. So I go through every one of the hearts and reset them all, okay? Just to make sure they're all exactly in the same state at that time. Now I come along, and remember, I have this special option here. You wouldn't have this in yours. That would actually shut the whole simulation off and just move to dumping and finishing if it were false, okay? So but by default, mine is on. And I ask, well, do I have an execution limit? If so, I'll execute the tick routine that hasn't really been changed, okay, other than that halt check that we already looked at, in a loop until we run out of instructions, okay, until we hit the limit. If I don't have an execution limit, I use a different logic altogether that waits until the cores, all the hearts have been halted, okay? So let's look at both of these and see how they work, right? So what happens in the first case? Well, if I got a limit, I want to go from 0, and I want to execute at most that limited number of instructions, okay? And I need to do that on every one of the hearts. I suppose what I should do in this code is ask if it's halted, stop executing. Because as written right here, if it halts, it'll still execute up to this limit, all right? So that's actually a flaw in this code. I'm going to look the other way right now because I don't really care. If you want to modify yours and put a check in here after you do this, which is essentially this right here, and then stop it right there, that'd probably be a good idea. But I don't want to mess with this because I already released it, and it doesn't really matter for this particular assignment. Anyway, I don't think we're going to worry about the execution limit, okay? It will be limited, but it'll still keep running until that limit is hit. What happens if we don't have an execution limit? And this is where the code is that I've been executing all along. Otherwise, I probably would have noticed the flaw up here. And what do we do in here? What we do is we have a Boolean value, and we assume that that at least one of the cores is not yet halted. In other words, we need to keep going. So what we're going to do is say, while it's not halted, just keep running. Okay? So what does this mean? We assume all the cores have halted, and then we run in for each one of the hearts and call the tick routine. So we're going to tick 0, then we're going to tick number 1, and then we're going to tick number 2, and so on. So what does this one line of code accomplish? Well, what it really does is it starts out as true, and if and only if every single core returns true from their is halted member function here, then and only then does this halted variable become true. That's when this loop ultimately ends. Okay? So while there's at least one core that is not yet halted, that's what this expression here means, then tick every single one of the cores while you're at and ask if all of them have become halted. That's how this loop works, okay? Which makes sense. Run until they're all halted, okay? And this is why this is a simple loop, and this is why the tick routine first asks if I become halted, and if the answer is true, you saw it does nothing and returns right away. By writing that code that way, it simplified this loop here. That's why I added that in there. So when I'm done executing all the code, again, this is just like our run routine, but I have to go through every single one of the hearts. And for each one of the hearts, I'm going to print out whether or not we were terminated by a break instruction. And then say, again, so you see the get ident in here, right? So for each one of the hearts, each one of the cores, it's going to print out, here's how many instructions were executed by this heart, this core, okay? When done with that, I do the usual thing, and I say, well, if I'm supposed to dump the stuff at the end, the Z flag, right? Well, in this case, I need to dump all the registers from every single one of the hearts. And I'm going to call the dump routine, which we looked at earlier, which includes the prefix of the ident in there, so we can tell which one of them is which. And then we're going to dump the memory. And the memory does not have it's not affiliated with any one of the hearts, and therefore it doesn't have this notion of an identity, right? Now we allocated an array of simulator objects, so therefore we have to delete the array of simulator objects, okay? So this thing here is how we achieve our multi-heart system. And that's all there is to it, right? There's nothing else hiding. If we want to write a program that runs on this thing, we can let every single heart do the same thing if we really want to, but that could probably cause all kinds of weird problems. What we would like to do is have each heart do something different. Well, at that point, that's why we need to have that instruction that we were looking at, that CRRS instruction. That allows each one of the hearts that's executing at the same time to get its heart ID number, which you can then use in an if-then-else or a switch or some kind of a branch table or something to differentiate the code that it's going to execute from the other hearts that the simulator is running. So that's what I changed in my simulator to allow it to run more than one heart at the same time, to create more than one RV32I object and run them all at the same time. Now keep in mind that this simulator itself is single-threaded. And that loop in the main, all right, and we'll look at it again, only does one tick at a time in either this loop up here or the one down here. So this simplifies a lot of weirdness that you would otherwise have to take into account on a real system, okay? And that weirdness is quite often taken into account in hardware, okay? So we don't need to worry about any of that stuff. When we call tick, this whole instruction will execute, and any memory it interacts with will be done before the next core or the next heart calls tick, and so on. In other words, we don't have to worry about the fact that when we go into memory, if we want to get or set a value, let's take a get 32, look what happens here. We call get 16, which calls get 8 and get 8. And then we call it again, which is going to call get 8 and get 8. This one does 4 independent interactions with our memory array. If all of those RV32I hearts / cores were literally executing at the same time, and one of them was writing some like a 16 or rather a 32-bit value in memory, and another one was reading a 32-bit value in memory at the same address at the same time, then what would probably happen is that one of them would get some of the updates. It could possibly happen that one of them got some of the updates that were perhaps already stored in here by the one calling set 32. While we're doing get 32 at the same time, we might get an inconsistent value, okay? Hardware is the same problem because all hardware is running at the same time all the time, okay? So we kind of look the other way right now with this simulator, given the simplicity that it is. If you actually built this in hardware, you'd have to include special functions and things that allow one of those CPUs, if it accesses memory 1 byte at a time or in chunks or however it works, to be able to lock out other CPUs or hearts or cores or I/O devices or whatever you need so that they don't interact with the same memory at the same time, all right? That would be an entire set of lectures in its own right just to cover that whole thing, okay? But certainly you can sit back and think about it for a moment and realize that that could happen and that someone has to deal with that. Well, we're going to deal with it by the fact that when we execute our simulator, and we go into our main loop, the entire one whole instruction and all of its memory interactivity will be done before we execute another instruction, all right? So we're not simulating all these weird nuances that could really confuse the death out of us. Taking baby steps here, people. Our simulator runs very simply, okay? All right, so let's see this thing work, all right? Now, I showed you before a bunch of example programs on how to build standalone programs. Now, one of the examples in here is this eBrake function that we looked at before, okay? Now, if we look at the eBrake application, all it is one instruction that just says eBrake and we're done, okay? So we can go ahead and compile this. This make file, does it have a run? Usually I have a run in here. So this thing has a, if I say make run, you can see it go. Now, this is running with my new simulator. I told it M10 and DIRZ, so disassemble it. I want to see every register dump. I want to see the instruction, okay? And Z, I want to see the registers one last time and the memory dump at the thing after the thing ends. So here's the eBrake executed after one instruction and so on, okay? If I do the exact same thing and I say I want 2 hearts instead of 1. Remember, 1 was the default. Just do the whole thing all over again. We're going to see now what happens with this ident stuff and everything else. So what happens in my new main, right? Same exact program that ran this one up here, right? So when I default with only 1 core, it makes it look just like assignment 5 and act like assignment 5. When I have more than 1 heart, we need to know which heart executed this instruction. So why did these registers get printed? Well, this is from heart number 0. And we made a simplifying assumption that hearts are going to go from 0, 1, 2, 3, and up like that, okay? Oops, I shouldn't have pasted that into my window. This down here, of course, is now printed by heart number 1. Okay, so what happens? We got heart 0 executed an eBrake and halted. Now we come down here. Heart number 1 executed this eBrake and halted, okay? When we're done, it goes to that loop at the bottom of the main where I said, okay, it printed out what Heart 0 did. How would it terminate? Well, it terminated with an e-brake, and it did one instruction. What about Heart number 1? It terminated with an e-brake after one instruction, okay? And then it's because the Z I print out one last time. Here's all the registers after the whole diagram finished. For Heart 0, here's Heart number 1, okay? And then I print out the memory dump. And again, it's not affiliated with any hearts, just like the disassembly, so you're not going to see the Heart number over here. And all this spew down here is because I accidentally pasted a bunch of stuff into my terminal, which is never a good idea. So what else can we do? There's all the garbage. I'm sorry about that. We can also run Heart if we wanted to. I don't know how many. Let's do, well, that's ludicrous. Let's run 4, okay? So now what happens? We got Heart 0, 1, 2, 3, and yeah, for 4 of them, that's 4. And they all stop. They all execute their one e-brake. They all have a post-mortem dump of all their registers after the thing is done. And again, the thing ends. Just for fun, let's go ahead and see if my program can tolerate 20 of these things. Of course, it should be able to run 20 cores. Wouldn't it be nice to have a computer with like 100 cores, right? Well, we can certainly simulate one, right? Here's the 99th core and so on. You can, yeah, this will take some scrolling, I guess, to see what's going on. It's nice to see that it worked okay. Core 99, all of them executed the one e-brake, and there they are all running, and there they are all e-braking and stopping. So this thing works pretty reasonably. All right, so this gets you a feel for what the simulator does when you try to run it with more than one heart and or 100 hearts and so on. If you run it with a default, or you say just give me one, it acts just like the simulator with it that we've been working with all along, and prints out the output accordingly. All right, so there's a walkthrough of the simulator that can handle more than one heart in the simplest, minimalist form. We just have to add that one instruction, so we can ask it what its core number is, or heart number is rather, and we need to be able to add these identities so we can understand what we're seeing when we print out all these status reports. All right, so that's all there is to that. Thanks for watching. I'll see you next time. Bye.